This is lecture 7, chapter 3, section 3.3. This is the lecture. In this lecture, we'll be dealing with couples and force couple systems. Now, in the past, a couple lectures on chapter 3, I've talked about how to find the moment about a point and the moment about a line. And this is just really an extension of that. And in this chapter, in this lecture, we're going to talk about the idea of a moment being a free moment. Now, first, let's define a moment of a couple. Now, there's a couple, the term couple and the term moment are synonymous. They're the same thing. The way the book writes it, sometimes it can be confusing, but just glue that to your forehead or put a Post-it note there that says they're the equivalent. Now, in this picture I've shown you, typically when we talk about a couple, we're talking about two equal and opposite forces in the same plane. So if you think about, for example, a star wrench. Star wrench is a four-sided wrench that had different size sockets on each one, used for different size nuts on cars to change tires. So the idea with the star wrench is you hold it against the tire when you're trying to change the wheel, and you'd push down on one side, pull up on the other. Now, if you're not familiar with that, that might be the best visualization. But if you think about a force, two forces equal in magnitude and separated by a distance d. And so we define them the same way. The moment is equal to r cross f. So r being any point on one force to any point on the other. And also it's typically only a couple is considered in two dimensions. And I believe there's couples in 3 dimensions, but we're not going to delve into that. We're just going to stick to two dimensions. Now, one of the things you'll notice when we're doing these problems is there's no defined origin. So if you have an object that has a couple acting on it, it's not specific to any one point. It's a tendency to rotate. So if you put a couple on a person, whether the couple was applied at their hand or their chest or their head, the magnitude of the force trying to rotate them would be the same. Now, assuming that you were a completely rigid body and didn't flex. So with that, it means that you don't have to pick a particular spot where you apply it. You just calculate it, and the good thing is that you can just add them together and you get the idea of the equivalency. Now, recall that the equivalency in your reading is talking about if you have a force and a couple, you create a new force couple system. Now, let's talk about that, because if you haven't seen the book, then that would be a new idea. Now, one thing I'll say is that in the book it does, if there are proofs, I don't believe they're in our book, that you can say two couples having the same moment, M, are equivalent. And so what does that mean? So to give you a little background, because I've been talking, is that if you have, say, a force like this, force like that, let's say that's 10 newtons, let's say that's 10 newtons, equal and opposite, and there's a distance between them. Let's say it's 5 meters. So we can see that 10 times 5 is going to give us a 50 Newton meter rotation. So you might ask, well, what about the force on this side? Well, it doesn't matter because if you were to say I'm going to apply my moment at this point here, then the distance from here to the force would be what? 2.5 meters times 10. And that would be from there to there would be 2.5 meters times 10. And so it'd be 25 plus 25 still gives you 50. So the moment is always calculated as force times distance, or R, excuse me, R cross F. Now, the idea of an equivalent moment would be if I had another moment like this, that say it was only 5 newtons, and I had that force there that was also 5 newtons, the distance between it was now 10 meters, then we could see that 5 times 10 is also 50 Newton meters, and it's also going the same direction, clockwise. So these two are equal. So that's the idea of the equivalency. just to give you a better visual. So let's go back to the slide. Now, probably the easiest thing to do at this point would be to do a numerical example. Now, in this example, you can see that there's a 40 Newton force at C, a 40 Newton force at B, and we're going to go ahead and try to calculate that. So let's go ahead and work through that problem and show you how this is done. Okay, now that you've seen that free moment problem, or that now you're familiar with the idea of the free moment, let's explain it a little more. So we know that in a couple, just like a moment, it can be represented by a vector. And so you can have ijk components. The moment can be moved to any convenient location. You can create your own origin wherever is needed. And this is more important in real life if you think about a machine system or some kind of a loaded system where having a rotational force at one part of the system may overwhelm the material.
Now we're going to do an example of a couple. So in this case, we have this rod that's connected at point A, and it has two parallel forces, 40 newtons at point C and another 40 newton at point B. Now, this is a sketch of the problem that I showed on the slide, so I would encourage you to use the slide to make a nice diagram like I have and draw it out, and if you need to pause the video, obviously do that. And then we're going to look at this from how we're going to solve it. So first, we're given that we have the two 40 Newton forces forming a couple, and we want to find the magnitude of the moment created by that couple. Now, in this example, I'm going to find the moment using three different methods. And after I do the three different methods, we'll discuss which one is best and why it's the best. All three will work equally, but some turn out to be a little bit more work than others. Now, in the first example, we're going to do it by finding components and then adding those components together. So what I have done is I have actually drawn a piece of the rod just from point B up to point A. In this case, what we have is the force that was originally applied here, the 40 newtons, and at point A, I've broken it up into Cy and Cx, so just the two components of the force. And what I'm going to do is I'm going to sum the moment about point B. Now, if I do that, then point B no longer matters. The force at it no longer matters because the distance is now 0. So in order to do this, I just have to look at how Cy and Cx have an influence based on the respective perpendicular distances. So again, this isn't equilibrium, so we're going to say the sum of the moments about B. That's going to give us our resultant. All right, and that's what we're looking for in Chapter 3. So how are we going to do this? Well, first off, let's look at our forces. So we know that we have 40 newtons coming up here, and we know that this angle drawn is 20 degrees. So I'm going to go ahead and write this out, that C sub x equals 40 newtons times cosine 20 degrees. And that's going to give me a value of 37.6 newtons. All right. Then I'm going to do the same thing for Cy. That's going to be 40 newtons times sine of 20 degrees. And that's going to give me a value of 13.7 newtons. And I won't worry about sig figs at this point. So I have Cx, Cy. Now I want to find these distances d1 and d2. Now we're told in the original problem that this distance is 270 millimeters. And we know that this angle here is 55 degrees. So if that's the case, then we know that if we say D1, D1 is just going to simply be equal to 270 millimeters, and then times the sine of 55 degrees. And that gives me a value of 221 millimeters. D2, that's going to be equal to 270 times the cosine of 55 degrees. And that's going to give me a value, in this case, of 155 millimeters. So now we're going to sum our moments about B. Move the paper up. So sum the moments about B. And what's that going to look like? Well, we know that CY here and its perpendicular distance is 2. So the moment's going to be CY, I'll write it here, CY times D2, right? And that's going to go in the counterclockwise direction with respect to B, so it's positive. And then CX, that's going to be times D1. But notice that CX is actually going in the clockwise direction. So we're going to subtract that one. We're going to say CX times D1. Sorry, this looks like a Z. Or 155 millimeters. And then that's going to be minus C sub X, 37.6. And then D1, 221. So that's going to be times 0.221 meters. Okay? And so once we get that, we end up with a value of about negative 6.21. Let me write over here, equals negative 6.21 Newton meters, thereabouts. So that's our first answer. So that's really what the couple creates. Now remember that this couple is a free couple, or a free moment. So that means that there's a 6.2 meter clockwise rotation trying to make this whole bar from A to C rotate. Okay, it's not fixed to any one point. And that's a major concept in this chapter of understanding moments, is that they're free. They're free. They want to make the rigid body rotate. All right, so now we're going to do part B. So we have the negative 6.21. So let's look at part B. Now once you see this, you'll see that there's a much easier way to do this problem. Now I'm going to go ahead and draw a line here, and let's redraw this structure. So what do we have? We have this line. Okay, move it up here, and we have a force coming up like this, and let's just exaggerate it, and a force going like that. And then we don't care about what's below there. Now we know that from angle standpoint, this is 20 degrees, this is 20 degrees. Now remember that if we want with a couple, we can always say if we have a force going that way and a force going that way, and we know the perpendicular distance, if that's F and that's negative F, then we know that moment, that free moment, is what? It's just equal to F times D, where D equals the perpendicular distance. Right? So what if we could find the perpendicular distance here? Well, that would make life a lot easier, wouldn't it? Well, we can, because if we were to draw a line from here to here, then that's perpendicular. So we know now we have a triangle. Here's our right triangle here. We know this is 270, and we know down here that this angle, the original drawing, is 55. Therefore, this entire angle here has to be 55. So if this whole thing is 55 and that's 20, that has to be 35. So now we have that angle. Sorry, it looks a little glitch there. Now we have that angle. And so what do we know? Well, our moment now is just going to equal 40 newtons times 0.270. That's the distance. And then the distance, of course, is the opposite. It's here. So it's sine of that angle, 35 degrees. And then we get an answer equal to, in this case, it was 6.19. And that might be due to errors. So I'm going to say it's about 6.20. All right, so a little bit of difference between this and this is probably an error on my part, but it's the same number. Now, one thing you'll notice is this is positive. Why is that? Well, we didn't account for the direction. Remember that if we just look at this, we can see that that vector going that way, that going that way, using the right-hand rule, doesn't really work out that close, but you can see that the rotation is going to want to be like that, or clockwise, which by default makes this a negative number. So here we have this method, here we have that method, essentially got the same number, just a little bit of difference from rounding error. Then we'll do the third method. So here's the third method now. So I've drawn a schematic of our bar, and now what we're going to do is here's point A, here's point B, here's point C. Now I won't label them fully like I normally do just yet, but we know that with this force here, then if we want to sum the moment about A, then we're going to have to count for both force C and force B. And so the easiest thing to do is to use the relationship we learned earlier and say the sum of the moments about A is going to equal then RB relative to A crossed with the force at B. And that's going to be plus RC relative to A crossed with the force at C. And so we can add the two together and we should get the same answer. Now this method is good, even though this is a fairly simple problem, this method works really well when you have three-dimensional vectors, because then the math takes care of itself and there's little visualization. So the previous way I showed you, finding the perpendicular distance, is good in 2D, but it's rather difficult in 3D. So what we'll do now is we'll just find out what are these respective values. So for one is, again, this is 55 degrees. We know this is 390, and this is 270. So the total distance here is, those added, is going to be 660 millimeters. And again, this is 40, that's 40, and we know again that's the 20 degrees and 20 degrees. All right, so again, it always helps to have a nice drawing. I'm doing this because I want to spend 10 minutes drawing while you watch, but when you do your homework, it's very important to take the time to make a nice drawing, and you only have to do it once. So what do we know? We have RB relative to A. So remember, B relative to A means we're going A to B. So if we're going A to B, we're going to go 390 is our hypotenuse, and we want to get there. So we know that that's going to be, in order to get there, that's going to be equal to 390 cosine 55. That's going to be our I, plus 390 sine 55. That's our J. So we got our A and J components for that. We know our force at B is going to be minus 40 cosine 20 degrees I and minus 40 sine 20 degrees J. All right, so there's our two values. Let's do the same thing, RC relative to A. And here we have the whole distance, 660. And that's going to be times the cosine of 55 degrees. Sorry, missed a 55. So let me erase that. So we got cosine 55 degrees I, and then that's going to be plus 660 sine 55 degrees J. Then we got force C, and that's going to be similar. It's going to again be, only since it's going up to the right, it's going to be positive. So it's going to be 40 cosine 20 degrees I plus 40 sine 20 degrees J. And there we have it. Okay, so we have all our components. Now, we just have to set them up. So we go ahead, we know that our moment about A equals, and so R, B relative to A, because it's always R cross F, never F cross R. F, B, we have I and J. And so in this case, we'll have our 390 cosine 55 degrees and 390 sine 55 degrees, and then minus 40 cosine 20 minus 40 sine 20. And then we'll do the same thing, plus, and then the other one will have RC relative to A. Sorry about that. And FC. And 660 cosine 55 degrees, 660 sine 55 degrees. All right. And then 40 cosine 20 and 40 sine 20. So in your own step, what I would recommend is when you get to this point here, go ahead and put numbers in for these. So for example, this should have been about 223.7, 319.5, 37.6. We know from the past 13.7. This is 378.5, and again, not worrying about rounding. 540.6, and again 37.6 and 13.7. So there's your numbers, and that would have been easier to plug into here, but either way works. So we go ahead and do our cross product. I'm not going to do that because I know you guys know how, but what we would end up with is this first one here would be 8.947, and this here would be a negative 15.142, which add together get about negative 16.1946. So again, you can see our final answer, negative 16.19. And so answers typically you want to write the moment about A equals 6.19, and you can either write clockwise or you can write it as 6.19 and write it negative. And of course, always make sure you have units. So one thing I didn't do here that I did is I converted. So even though I had 660 here, after I got through with this is actually in Newton meters. And this is Newton meters. And you'll probably do that more regularly as you get used to it. If I do it without saying, that's why. Kind of get ahead of myself. But so that's the problem, though. You can see that each three method got you the same answer. Obviously, B was much easier, just having to do a little tiny curve like this, or little triangle. And the first method wasn't so bad either. But this method here is the tried and true. This will always work whenever you do something. So please remember that, and thank you. And that's the end for this example.
We add is we always want to describe an IJK. So just like we added forces, if you had, let's say you had 10 moments. So if you had, moment 1 equals 6i plus 4j minus 3k. And again, this is in 3 dimensions. Moment 2, moment 3, and so forth. And that equals 5i plus 4j plus 3k and 10i plus 10j minus 10k. So we know that we can just add them like we would any other thing. So we get negative 10k, that's 18j, and 21K. I'm sorry, 21I. So that's just the sum. And so it's the same thing with what we're doing here is we just add everything together. Now this is where it's hard to do this with a video as compared to a live classroom, because I'm not able to look out and see some puzzled looks. So that's why I encourage you is to look at the material, look at the examples, and if it's still not making sense, please log in and to the Zoom on during office hours and let me explain it in more detail. So going back to this, let's talk about the idea of the force couple system. Now initially this seems kind of weird, but after we do an example and I explain it, I think it'll make more sense. Now, imagine you have a rigid body that is, and this diagram actually is very good for explaining this. So looking at this, let's imagine we have this force at A. And so there's a force applied at A. Now, for whatever reason, we don't want the force applied at A. Maybe A is too thin or too weak, whatever. We want to move it to O. Now, we can't just move the force from here to here because, again, that's going to change the loading state of this. And so we want to be able to move the force from A to O without changing the loading, without doing anything external to it. So the idea with this is, first, what you do is you add an equal opposite force of the same magnitude to O. So now if you sum the forces in the X and the Y here, and you sum the forces in the X and the Y here, they're still equivalent because these two cancel. Now you notice that if we add an equal and opposite force here, that this negative force and this force do what? They form a couple. So we can then determine the moment created by these two forces by doing R cross F. And so that R cross F gives us a subsequent moment, O. And that moment about O is, don't worry about the perpendicular sign at this point, but that moment about O is added to that point when we move it. So as long as if we move the force to O, as long as we add the moment with the magnitude of R cross F to that point, then everything is equivalent. So, and that's a lot to wrap your head around instantly. But again, this is one of those things where if you follow the math and you do it, it'll probably make more sense after you do a few problems. So now that we've done that example, you can see how we were able to just simply move the force from A to O and add that moment, and we were done. And so this slide just says that you're not limited to only doing it once. So for example, I could start at my original force could be at A, and maybe I want to move it to O. So just like the previous slide, but after I move it to O, I'm fickle, I changed my mind, I want to move it to O prime. And so what that says is that you can move the force all around, and you can really almost, the best thing to think of is just ignoring these intermediate steps. Because in a way, if I went from A to O and then O to O prime, that would be the same as just going from A to O prime. The idea would still be the same. If I move the force to O prime, I have the force, and then I have this moment that is created by R prime cross F, and that's it. So I'm not going to have you do calculations where you move it multiple times. That's not really necessary, but if you had to, you could. So we've talked about so far is we've talked about the idea of a force couple system. And in the last example, I believe I emphasized, and that one you might notice was recorded at a different time than this whole lecture. I was trying to experiment with Premiere. And so this force couple system, the idea with that is the wording is very specific. It'll usually say something like replace the force at A with an equivalent force couple system at, let's just say, C. So if you see that writing specifically, then you know your final answer is going to consist of, because it's an equivalent, first off, the first thing you want to do is write your force. So whatever the force is at A, it's usually given to you in IJK, or it's given to you as a magnitude with directions. That's the first thing you're going to do is figure out what is that force in IJK, because that is part of your answer. If you leave that out, you don't get it all correct. Then the next thing is just going to be the moment at C, and that's going to be equal R C relative to A crossed with the force. So remember that your vector is going to go from wherever the location is to the old location. So for example, in the previous example we went, the force was at A, original, correct? And we wanted to move it to O. So we went from O to A. And so in that case, we want to go from here, we want to go from, C to A. Sorry, I think that's backwards. A relative to C. All right. So always go to the force. So if you have something where this is that's where your force is, that's where you want to go to, and that's A and that's C, then your vector is always going to be R C relative to A. So you're going to go from here to here. Okay? Remember that. All right. All right, so let's look at this example. Now this example is a little different. Remember, we've talking about equivalent force couple equivalents, but you'll notice that in this example, all we have are couples. You have these, we have P and minus P. We have the 240 pounds at an incline, and we have the 16 pounds up and down. Now, before you even start anything, look at this and realize that the 16 pounds are creating a negative rotation about the z-axis. So if you take your hand and you hold your thumb away from you and you curl your fingers toward you, you'll see your thumb is pointing away. And that's the rotation direction of the 16 pounds. It's wanting to go clockwise relative to the negative z-axis. So it's negative. Or it would be, yeah, so it's negative. And then if you look at the P is creating a positive rotation, because if you take your hand and curl it with your thumb pointing up, it's going to curl around the y-axis. So P curls around the y-axis. Now, the 40 pounds doesn't curl on either axis. It's got part of one. And so that's where we're going to use the R cross F. And so first and so once we do that, we'll have the moments for each of these. There's 3 total, and then we just add them together like components, and we're done. Simple as that. So let's work this one out. And you can try, if you want, to do this. If you feel confident and you want to live on the edge, maybe spend a few moments, try to work this out yourself. If you're going to do that, first thing I do is figure out the distances between these and then go from there. Okay, so 1, 2, 3, you're going to pause now. Okay, and now I'm back. so here we go. We have the problem. I printed it out. Maybe it'll be a little easier to see. So let's go ahead and work this thing out. Now, so the first thing, we want moment total. That's going to equal M1. These are all vectors, M2 plus M3. So we're trying to find this. We want the single equivalent couple. So notice there's no force because all the forces cancel. If you add all the forces together, the sum of the forces are 0. So that's why there's no equivalent force in this. Now, once we have that, let's define each force. So we're going to say that F1, force 1 is going to be the 16 pounds. F2 is going to be the 40 pounds. And actually, I'd probably leave those as scalars because I'm not going to put any direction on them yet. And then F3 is going to be the 20 pounds, or the P. Okay, so there's P, 20 pounds. All right. So let's go ahead. Now, it's just a question like before, was we're going to find the magnitude of this, magnitude of that, magnitude of that, and then we'll go ahead and add them together. So the first one, M1, let's look at that. So we defined F1 as the 16 pounds. Notice the 16 pounds is going up and down. So now this is where, this is a point, and this might, some of you may already realize this, but this tends to be a point that students have struggled with in the past. So I'm going to take a few seconds to explain. Now, when you're finding the distance between the two here, you have a choice of going from this force to this force, or this force to this force. So remember what we said is you always go to the force. Well, how do you know which force to go to? Well, let's look at that. So if I start here at this 16 pounds, and remember, since the 16 pounds is on the y-axis, it's extended all the way down to the origin. So it really doesn't have a y component to it. And so the distance, if we go from here to here, is what? A positive 30 inches. So if we write that as R C relative to O, right? Going O to C, O for the origin, right? Then we have a 30I. So 30I, okay? It's our R, and then we're going to cross that with the force at P. Now the force at P is what? It's going in the negative y direction, isn't it? And so we're going to say negative 16J. All right? Now, if we do that, we know that if we do I cross J, then normally that's a positive, but because it's a negative, it's going to be a negative answer. Now you can use, and I'll come back to that for a second, but remember what I showed you, you can have I, J, K, and if you go that way, it's positive, and if you go that way, it's negative. So if you don't remember, and when you get old like me, it's easy to forget, but I cross J going this way is a positive K. So what I do is that equals negative 480 inch-pounds K. All right, sorry, negative 480 inch-pounds K. And so if I had done it the other way, let's say I had started here and gone there, you can see it would have been the same, because what would have happened is if I'd gone from here to here, I would have gone negative 30I crossed with a positive 16J, which still would have given me I cross J, in that case, a negative 480 inch-pounds K. So it doesn't matter which one you go to, okay? And that's if hopefully that makes sense. So we have the first one. So let's go ahead and look at M2. Now that's the M2 is the 40 pound. All right. Now, make sure I can try to get that all on the screen. So now notice the M2, the 40 pounds, it's if we go, we can pick, we can either go from B to E or A to D. Doesn't matter. You're just picking, or anywhere in between. But when I did it, I went E relative to B. So I said M2 is equal to R E relative to B. And then that crossed with F2. And so that is going to be vector because I'm going to give it a place. And so if I go E relative to B, then let's write it up here again. Sorry, we're running out of space. So R E relative to B is equal to what? If we go from B to E, we go 15I, but we drop 5J. Now, how do we know? Because we know that from here to here is halfway, and we know if we go from B all the way to C, we drop 10. So halfway, we drop 5. It's a similar triangle. So we write 15I minus 5J. All right, so that's that. So I come down here, and I'm going to do the heresy again, have the double equals, and I'm going to say, for lack of space, 15I minus 5J crossed with, and then because I went to it, what's my force? Now the thing is, my force, I have a force, even though I went from what? I went from B to E, my force isn't just simply IJK. I'm sorry, it's not just simply an IJ or K. We have to figure out what is this force direction, okay? So let's leave that there and come back. So if we want to figure out the force direction, we know that we have force 2 is going to equal 40 pounds, and then it's going to be multiplied by 5J minus 10K, all divided by 5 times root 5. Now, where did I get that from? Again, pull this up a little. It's a little blurry, but hopefully you can all see it there. So the 5J, because I had F2, right, I went from, so E relative to B, I went from B to E. So because I went to this force, I have to use the components of where this force is going. I could have done it the other way. I could have gone that way. That would have changed these, and it would have changed 40. It would have been going down. Now, notice that in the, from going from D to E here, the 40 pounds, it goes up in the J, has no X component because it's parallel to the axis, and it goes in the negative K direction. So it's going up in J and negative in K. That's where I got the 5J minus 10K. So you can see the minus 10 here, and we already know that halfway point is 5 inches from the base. So this is just the square root of 125 here. So we go ahead, multiply through, and we get 17.89 J minus 35.77 K. So we go ahead and we'll set it up. M2 is going to be equal to 15, negative 5, 0, crossed with 0, 17.89, negative 35.77. Sorry, it's getting a little. So all I did was I took the R E relative to B and my F2, and there's my I, J, K. Okay. So hopefully that's clear enough if you have to rewind it, but that's the process. So I know you know how to do that. So when we go ahead and find our answer, we end up with M2, let's do it this way. M2 gives me a value of 178.9 I plus 536.7 J plus 268 268.3K. Again, not worried about sig figs at this point. So that's M2. Now let's bring in M1, right? So we know M1 was equal to what? It was negative 480K. And then we'll bring in M3 at the last, and then we'll add them. So let's leave that there, that space for now. So let's figure out M3. So let's come back up here to M3, and we'll go back again. Now M3 was the 20 pounds. And this one's another simple one like F1. Because again, even though P is at A, it can be extended all the way back to the origin like we did that. And so that's very blurry, I apologize. Let's see if I turn the light on. That doesn't help. Okay, hold it up. So again, if you extend P all the way back to the origin, then really the only distance between P is on the x-axis. That's what I'm trying to say. Okay? All right. So we know then that the distance with P is just going to be 20 or 30 in the I, right? So if we go from one to the other, again, if we go to, this is similar to before, if I go from O to C, then what do I have? I have a negative P, right? It's in the negative direction. So this is negative 20K, and this is 30I. So basically, for M3, I have 30 cross negative 20. Okay, so let's write that out. Here. And again, if you have this printed next to you, you can see it. But so M3 again was 30I crossed with negative 20K. All right. So the negative 20K gives us 600 inch-pounds in the J. And so if we look back, how did we get that? If we look back here, so 30I cross negative 20K, if we do I cross K, we're going clockwise, so that would give us a negative J. So I cross K goes clockwise, negative J. The negatives cancel, that's why it's positive. All right, so 0, 0, 0, 600, 0, right? And so now we can add all that up and we get our total and we're done. All right, so our total then is, sorry, I should have left a little space. Our total ends up being 179.9 I plus 1137J minus 212K in inch pounds. And there's our answer, the right sig figs. 4, because it leads with the 1, 4 leads with the 1, 3 leads with the 2. Okay? So I hope that made sense. You can go back and look at it again. I would encourage you to. Now, one other thing with this is sometimes it'll ask you, like in this problem, it may be good enough to just add all 3 couples together into a student couple, but this one says specify magnitude and direction of its axis. So how do you do that? So that one last part is just simple vector stuff again. So if we bring that down, we know that the magnitude, right? It wants the magnitude, then that's just going to be what? The 179.9 squared plus 1137 squared plus the negative 212 squared, all square root. and that's that. And so I get a value of 1170 as my magnitude. So there's my magnitude. And then if I want the angles, I do the same thing as before. I know that theta x is what? It's equal to the inverse cosine of 179.9 over 1170, and so forth. Theta y is inverse cosine of 1137 over 1170, and theta z inverse cosine of negative 212 over 1170. So this stuff here, if you see magnitude and direction angles, that's what this is talking about. I probably won't do this in the future, or I may just write the answer because you know how to do this. This is just basic vector manipulation. So this gives us 81.2 degrees, double equal sign heresy. I can get away with it though because I'm at home, so you can't scold me. But there it is. Okay, good. Let's go back. So that's that. So that's the first one on the worksheet. Now let's look at this next one. So go ahead and look at this problem now. And we always call them problems, and that has like a negative bias off the bat. So you could call them assignments, challenges, big fun. I don't know about big fun, but so and I'm sure you guys being cooped up by yourself after a while, you start to get a little stranger than you normally are. So bear with me if some of this long, incoherent rambling starts to get a little weird. All right, so looking at this one here, equivalent force couple system from a force couple system. Yeah, a lot of words. Now this is really no different than what you've done. The only difference in this one is you have this force F and you have a moment already in there. So you're asked to find an equivalent force couple system. Now let's ignore this moment for a second. Let's ignore the moment for a moment. How about that? So let's pretend that's not there. If that was not there, this would be just like the second example I did, where you have F going from A to J. So you'd first convert that to a vector, and then you were trying to move it over here to H. So you would just figure out what is the vector going from H to A. So you have A relative to H. A, do the cross product, and that would be it. So the only difference with this one now is that once you get that moment from H to A, you now have to add this moment to it also, because it's a vector, you can add it. So your final answer is going to be this force, the moment that you got from moving this force over to H, plus whatever the components are of this moment. All right. So if you're up for the big challenge, then go ahead and try this problem, and try it out. I would very highly encourage you. Again, when I do these examples, I would again encourage you to pause, try them out, see how far you can get, and then come look at it and see how it is. All right. So you're going to try it. Okay, so you've had a chance to work on the problem. Let's go ahead and look at this one. Now, we have our drawing. So we know that our moment at H, the equivalent moment, this is our answer, is really, it's going to be equal to the moment at A plus R A relative to H, going from H to A, crossed with the force F. That's going to be what we were looking for. So let's go ahead then and figure this out. So first thing we should probably do is figure out what, and there's no real order you have to. You could figure out the moment first if you want to. But the first thing I'm going to do is figure out what is this vector AJ, because we need to determine the force to that. So let me go ahead, do that up a little bit. So if we look at that, we know that the force is just going to be 46 pounds, and it's going to be 18 in the I minus 14 in the J minus 3 in the K. And I'm going to divide that by its magnitude, which turns out to be 23. All right. So this gives me a value of 36.0, negative 28, negative 6. So there's my value in pounds. So I have my force. Then I'm going to go, I need R, A relative to H. In that case, that's going to be 45I plus 14J. So now I have what I need. I can go ahead, the moment H from moving, it's just going to be R, A relative to H crossed with F, okay? So what I'll end up with then is this, if I go ahead and do the cross product of this, which I know you guys can do, so I'm going to skip this showing the cross product. We know we have the values. So what I'll end up with is MH equals negative 84.0I plus 270K minus 1764K. Sorry, this is 270 plus 270J. Always write with a pencil in my class. There you go. So that's the moment about H. Now, the other moment, in order to get that, the other moment is simply multiplying. You have this 1800, I'm sorry, this 2120 up here. So let's look at that. So we have the 2120, and then we're going to multiply that by the unit vector, right? The unit vector AC. So that's just going to be AC over AC, isn't it? So we need the 2120 times AC. So what's AC going to be? It's going to be negative 45I, right? Because we got to go back here, and we're going to go that way. So that way is 25 plus that little 3. So it's going to be minus 28K. All right. And so if we square root that, it turns out to be a nice triple triangle, 53. And so what we end up with is we multiply the 2120 by this, we end up with negative 1800I and minus 1120K. So all that was putting that moment into vector form. So if I come up here, then I call that M, just call it M2. And I have my negative 1800 I 0 and negative 1120K. And that's pretty much it. Now I just need to add that together. I get negative 1884 I plus 270J minus 2.88 times 10 to the third K. Now that's kind of Mickey Mouse to have mixed units. I had 2884. So what I could do to keep the sig figs, I could say 2880 and call that not a sig fig. So again, best, on an exam, if you put a 0 there, that's fine. I don't want to be too much of a sig fig Nazi, but this follows our convention. And so we know that's going to be in inch pounds. So that's our moment. And then of course you have to include your force. So remember, that when you're writing your final answer, always also have the force. And if you write it like this, that's fine. Okay. And so that's that. So that's dealing with an extra moment. And so you can think about this problem is that it could be as complicated as you want. We could have 10 moments. We could have 3 forces. And so you just systematically work through all of it. I'm not going to give you that because it's kind of like if you do multiplication tables when you were in grammar school, after you learn how to multiply 3-digit numbers, do you really need to do 1,000 of them? Probably not. So I leave it to you to decide how comfortable you are with the material. If you need more examples, then there's plenty. I know the solutions manuals are out there for this book. I'm sure you found it. I know that you can just copy them if you want on the homework. That's why I don't grade it for the actual correct answer. I highly encourage you to not do that because it will show when you take the test, but I can't stop you. Anyway, I do have one more example. And if you're satisfied you understand fourth couple, then you don't need to watch it, but if you'd like to, you can. I'm going to go back and show it to you.